Hey guys, welcome to your next lesson. Today we're going to start talking about inference for linear regression. So I'm going to first try to explain how it works. So as we know, we have this massive list of 162 basketball players, and we're going to treat that as our population. And if I actually did a scatter plot of all 162 points, so this isn't really 162 points, but you can imagine if I had all 162 points, we could do a regression for those 162 points, and we would get a regression line. Notice I'm labeling it the true regression line. So this would be the regression line for all 162 players. And we'd have a whole bunch of players that are averaging 8 shots a game, a whole bunch of players that are averaging 9, a whole bunch that are averaging 10, and so on, right? So we'd have this mass of points, and it would have this true regression line. And we could sample from this population, which is what you did. And when you sample from the population, what you're doing is you're basically choosing 12 of these 162 points randomly, right? So maybe you chose this one randomly, and maybe this one, and then this one maybe, and then this one, and then this one, this one, this one, this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 3 more, this one, this one, this one. All right, so maybe those are your 12 points, right? So your sample would consist of those 12 points, right? So whatever that's going to look like here when you plot your sample, right? I'm just going to do what it kind of looks like, I guess. Okay, so it looks something like this. But that's the idea. So you're taking 12 points out of 162, and that's your sample from your population. Now, will your sample have the same exact regression line as the population? And the answer is no, it won't. But it should be relatively close because you're randomly sampling, so it's a representative sample of all of these 162 points. So whatever this regression line turns out to be, it should be not identical to what we're calling the true regression line, but it should be similar to it. It should have a similar slope, not the exact same slope, but similar slope. And of course, everybody did this, so you all sampled 12 random players, so you all are getting different slopes and different lines, but they should be relatively in the neighborhood of what I'm calling the true regression line. Now I'd like to talk about this in a little bit more abstract way with a bizarre looking picture. So let me show you that. So in this picture, and by the way, it's hard to draw this three-dimensional picture, but I did the best I could. If you want much better pictures of what we're describing here, just go to page 742 and 743 in your textbook. You'll see much better pictures than what I came up with here. So this red line here is what we're considering the true regression line. So we have values of x, and you can think of this in terms of our basketball example, 8 shots a game, 9 shots a game, 10 shots a game, 11 shots a game, and so on, right? We'd have a whole bunch of players that have different points per game based on 8 shots a game. We'd have a whole bunch of different results for players that shoot 9 times a game, and so on. But here's what we're saying. So in a perfect world, what we're looking for, so this is going to lead to the conditions we're going to talk about for inference for regression. So in a perfect world, what would happen is this. All of these y values that correspond to this x, right? And you can think of it as all of the average points scored for all the players that take 8 shots a game. If we average them together, the average of all of these would actually be on the true regression line. Same thing at the next value. So think of that as like 9 shots a game. The averages of all the points would also be on the regression line, as with this. So all of these averages would be on our true regression line. And in addition to that, these orange things here, these are supposed to be normal curves. So not only is the average of all my y values on the line, but at each value of x, the different values of y are normally distributed around that average, right? So that's what these are. These are normal curves like this. And they come along with a standard deviation. So if we went one standard deviation to the right, this would be what we're calling sigma. And that's very analogous to what we were calling S before, right? S was like the prediction error, right? And that's kind of what this is, right? It's the typical error that when they dance around whatever the average is for, let's say, 10 shots a game, which is on the line, we're going to dance around it in a normal fashion with this standard deviation. So sometimes we'll deviate by more than that, sometimes by less than that. But in an ideal world, these averages are all on this line, and the individual values at each x value, the individual y's, are normally distributed around that average for all values of x. By the way, the equation for what we're calling the true regression line looks like this. It's the mean of your y's is equal to, so the average of all these y values, right, is going to be equal to, instead of a plus bx, alpha plus beta x. So that's the equation that we use when we're describing this true regression line. Now, in reality, we never see the true regression line because the population sizes are so huge, right? So in our case, we're using an example with 162, so it's not that huge. So I guess technically we could put them all in the calculator and see what this line is. But typically we can't see what this line really is. So what we do is we sample from that population, just like we're doing here. And we're taking 12 out of that 162. And we're going to get a regression equation for our sample. So for the sample, so not this, but for our sample, we're going to get our y hat equals a plus bx. And when we do this, our a value is going to be an estimate for whatever the true alpha is. And our b value is going to be an estimate for whatever the true beta is. And by the way, the s that we get, right, that's that prediction error will be off by, on average, that's an estimate for what the real sigma is, okay? So we're going to talk more about this, but this picture is important because it'll help us in our discussion of what follows, which is the conditions for regression inference, and that's coming your way next. Okay, so let's talk about conditions for regression inference. Now, there's a lot of conditions to check here, but we have a nice acronym to remember them, and it's LINER. As you can see, L stands for linear, I stands for independent, N for normal, E for equal variance, and R for random. Okay, so let's talk about each of these conditions. And the first thing we're going to do is talk about what they are. And then we're going to talk about how we check them. Okay, so the first one up is the linear check. So this condition here is going to be the following. The relationship between x and y is appropriately linear. So we don't want a curvy relationship, we want a linear one. So that's the first condition, what it is. Now the second one is independent. Now in this course, independence is confusing because we use it in two different reference frames. One of them is when we're taking two samples and we want those samples to be independent. The other one is, we take a sample and we want the observations within that sample to be independent of one another, right? And that's the type of independence we're talking about here, right? So we'll say here the condition is that individual observations are independent of one another. So individual observations independent of one another. So independent of one another. Obviously, it's not the independence between samples because we're not taking more than one sample here. We're just taking one sample, right? So we're talking about the independence within that sample, the observations. So the individual observations are independent of one another. Normal, so the response y varies normally at each x value. And that's what this picture is bringing out, right? So these y values are all varying normally at each x. So that's the normal condition. Next up, we have equal variance. So the standard deviation of your y values, we'll call that sigma, right? So we saw that in the picture on the other side of the board, is actually the same at each x value. So I didn't mention this before when we looked at the picture. So let's talk about that in a little bit more depth here. So the standard deviation of the y values, this thing we're calling sigma, is the same at each x value. So taking a look at our picture, we're not only saying that the y values are varying normally at each x value, but the standard deviations are equal. So whatever that standard deviation is there, it's the same standard deviation here. Whatever the standard deviation is in those two places is the same one that's here. So we have the same variance at each x value. That's why we're calling this the equal variance condition. So the standard deviation of the y values, this thing called sigma, is the same at each x value. And of course, random, I think we got this one. The sample is randomly taken. Or randomly selected. Now, this is what the conditions are, but it's not how we check them. So the next thing we're going to discuss is how we check these 5 conditions. These are just a list of what they are. So coming your way next is how we check these conditions. Okay, so we've seen what the conditions are, but now we're going to see how we check them. So starting off with that linear condition. So remember that what the condition was that the relationship between x and y is appropriately linear. And we know how to check for that, right? We look at the residual plot, and we're hoping to see a lack of a pattern, right? So that's how we check this. So we look at the residual plot. And if there's a lack of a pattern, so where a pattern is bad, that means it's potentially a curvy relationship. So we're looking for the lack of a pattern. So if there's a lack of a pattern, the relationship is appropriately linear. Appropriately or a linear relationship is appropriate, right? So that's what we're looking for. That's how we check that condition. We look at the residual plot, looking for a lack of a pattern. This is independence within the sample, right? So remember, so if we use our example of the 162 players, we're sampling 12 without replacement, right? And whenever you sample without replacement, you don't have true independence. But you have that, what I call sort of independence, or pseudo, that's P-S-E-U-D-O, pseudo independence. You'll have that if your sample size is small relative to the population. How small? Less than 10%, right? So we check the 10% condition. And of course, if sampling without replacement. That's without replacement, which we usually are doing, right? And that's what we're doing for our basketball players, right? We didn't want to choose the same player twice. So we check the 10% condition. So we have this sort of independence, this good enough independence when sampling without replacement. Okay, normal. Now this is an interesting one because here's what we really want. We want the y values to be normally distributed at each x. But if we're sampling only 12, which is what we did with our basketball players, I'm only going to have maybe 1 or 2 players that shoot 8 or average 8 shots a game, maybe 2 players that average 9 shots a game. Maybe we won't even get any that shoot 10, maybe 1 that shoots 11, a couple that shoot 12. So there's no way that we're going to be able to test normality at each X value in our sample, right? Because the sample is going to be too small to do it. So what we do is we group all of the residuals together, right? And that's what we're talking about here, residuals, right? So we want the residuals to be normal, okay? So if the residuals are normal at each X, that's really what we'd like to see. But again, we're not going to have enough values at each X. So we just pool them all together. And we look at all of the residuals as a group. And if the residuals are roughly normally distributed, not perfectly normal, but roughly normal, then this condition is met. Okay, so let's write that down. So how do we check this normal condition? So we'll do maybe a stem plot, or maybe maybe not a stem plot. Let's just say a histogram. That's usually what we're going to use. So we'll look at a histogram of all residuals in our sample. Again, because we don't have enough at each X value. So we'll just take a look at all the residuals in our sample. And if we have, symmetry, lack of outliers. So if we have symmetry and lack of outliers, the condition is met. So we look at a histogram of all the residuals in our sample. It doesn't have to be a histogram. I guess you can do a stem plot or something like that. So histogram, in fact, we'll add that to that, stem plot. Anything that gives you the shape, right? A box plot wouldn't give the shape too well, but a stem plot does an okay job. So a histogram or a stem plot of all the residuals in our sample. If we have symmetry and lack of outliers, then the condition is met. Again, we're not looking for perfect normality, but we don't want to see major departures from normality like severe skew or outliers. Okay, equal variance. So in this case, here's what we're looking at. We want to vary by the same level at each X value, right? And how are we going to check that? Well, what we're going to do is this. We're going to look at the residual plot again. So we actually look at the residual plot twice. Once to check this condition, and a second time to check this condition. Because when you think about a residual plot, right, centered at 0, and then you're going to have, let's say, at 8 shots a game, 9 shots a game, 10 shots a game, or whatever. And you're going to have a residual plot. It's going to look something maybe like this, some above, some below, whatever, right? And we'd like to see like equal variance at each one. Now, do I have exactly the same variance at each of these? No, but we want them to be roughly the same. So this would be something that would be good enough. However, if we had a residual plot and we looked at it and it looked like this, where we had like a big spread at 8 and a not so big spread at 9, or a smaller, and then as we went further to the right, if we saw something like this in our residual plot, that would be bad, right? Clearly not equal variances. Not only that, they're actually decreasing as we go up, right? So we're not looking for perfectly equally variant at each X, but roughly equal variance at each X. So yes, we are going to take a look at the residual plot again to check this condition. So check residual plot. For roughly, and we're saying very roughly, because we're never going to see equal variance exactly. So check residual plot for roughly equal variance at each X. So there's the equal variance check right there. And random, I think we know how to do this, right? Is your sample randomly selected? So is your sample randomly selected? All right, so now we've seen what the conditions are, and now we see how we check them, right? And again, this is the acronym liner. Okay, so the next thing we're going to do is we're going to take a random sample of 12 basketball players. So I took a random sample, you've printed it out, and let's use it to estimate what this true regression line might be. So that's coming your way next. All right, so as we said, the true regression line for, let's say, all 162 NBA players in our massive list is going to be mu y equals alpha plus beta x. So what I want to do is estimate alpha, estimate beta, and also estimate sigma using our random sample of 12 NBA players. So I randomly sampled 12. You've printed out that sample of 12. And I want to estimate those three things. Obviously, A is going to be our estimate for alpha. B will be our estimate for beta with our regression line. But remember, S is going to estimate sigma. So just to remind you how we calculated S, right? So we got to S because we wanted to find out like the average amount we were off by. In other words, our average residual. But getting the average residual, remember, was problematic because the positive residuals will always cancel with the negative ones and you're always going to get 0. So you can't add them up, right? But you can square them, right? So the way we did this was we took the sum of all of the residuals squared. And we have 12 NBA players, so you might think we would divide by 12, but you might remember that we did this weird thing where we divided by not n, but n minus 2 instead. Okay? So we're doing that, by the way, because we have these two degrees of freedom. Like we need to know alpha and we need to know beta as well. You don't really have to worry about that part, but this is how we're going to calculate S, which is going to be the sum of the squares of the residuals divided by n minus 2. So obviously it's calculator time, so get your calculator out and your printout, and let's get to it. Okay, so we'd like to estimate alpha and beta for the regression line, the true regression line, by using our sample of 12. Now this time it truly is a random sample. That first sample of 12 we looked at the other day, I intentionally picked out 12 players so that the slope would be actually higher than what it actually is. But this is a representative sample. So this is 12 randomly chosen players. So let's start to put them in the calculator. So let's hit stat edit. And I want to use L5 and L6 again. So let's clear out the McDonald's data that we had in there. So we'll clear out L5, we'll clear out L6. And for this random sample of 12 players, in L5, we will put in the shots per game for each player. So John Morant is first, 16 shots a game. And then next up, we have Reggie Bullock for the Knicks, 8 shots a game. All right, so put all of those shots per game in L5, and then put all the points per game in L6. Pause the video to give yourself time to do that, and I'll do the same. Okay, so now that we have the data in there in L5 and L6, let's run the regression. So we hit stat calculate, choice 8, and we have our X variable in L5. We have our Y variable in L6. And we'll store the regression equation in Y1. Why not? And then we'll hit calculate. Okay, so we have our values here. So the value of A is negative 3.20. Our value of B is 1.51. So that's 2 down. Our A and B are going to be estimates, or what alpha and beta are. But now I'd like to get S. So S is the sum of the residuals squared divided by n minus 2. So now that we've run the regression, it has stored the residuals in that list called resid. So if I hit stat edit, I might as well just put them in L4. So let's highlight L4, hit enter, and then second list, and then find resid in your list. And it'll put all the residuals in here. If we added all these up, we'd get 0. So we're going to square them all. So let's put the squared residuals in L3. So we highlight L3 and we hit enter, and then L4, which is above 4, and then we're going to square every member of L4. All right, so these are all positive, of course. We squared all the residuals. Let's find the sum of all the values in L3. So I'll hit second quit to go to the home screen, and then I'm going to hit second list, and then go to math. So second list, which is above stat, and then over to the math menu. Choice 5 is sum. We want the sum of, I think it was in L3. Yep, sum of all the values in L3. So the sum of all the sum of our squared residuals is this number. So our S is going to be 39.675 divided by n minus 2. So we sampled 12 players. N minus 2 is 12 minus 2, so that's 10. So we're going to divide by 10. However, I just realized I forgot something pretty important. When we square the residuals, right, we're making the number too big, right? So if I just divided these the way they are, I'm going to get something that's too large for S. The formula here for S, and I forgot it, my bad, all of this is under a big square root. So add that in there. Sorry about that. Of course, that's under a big square root. So our S is going to be the square root of the division of these. Well, we don't need a calculator to divide that number by 10. This is 3.9675. Oh, I guess I don't need a numerator anymore. So we divide by 10. It's just going to be the square root of 3.9675. So it's pretty much almost like the square root of 4. So I know to the nearest tenth, I think this turns out to be 2.0. So that's our value for S, and that's going to be our estimate for what sigma is. All right? But let's go back to the board and capture these estimates and talk about what they mean. Okay, so again, I apologize for missing that big square root. That was a pretty big miss on my part there. So big square root is a part of the formula for S. Okay, but we have our values. We have A, we have B, we have S. So let's talk about what these three things really mean in context, right? So alpha is the number of points scored or the predicted number of points scored for an NBA player who averages 0 shots per game. So 0 shots per game. And we're talking about alpha here, right? So this is really describing all 162 players. And our estimate for alpha is this, negative 3.20. So we've mentioned it before. The y-intercept typically has no meaning. There are some cases where it has meaning, but usually it has no meaning. That happens all the time. And of course here, it's meaningless, right? But that would be what the interpretation of alpha is. Now beta, that's the one that will have meaning. It always does, right? So beta is the increase predicted, I keep forgetting that word, is the predicted increase in points scored per game, or points per game, for each additional shot taken. So beta is the predicted increase in points per game for each additional shot taken. Again, it's beta, so we're talking about all 162 players. And this is a meaningful number, right? On average, what's the predicted increase in points per game for each additional shot a player takes? So our estimate for beta is this, 1.51. Now, keep in mind, do we believe that beta is 1.51? No. Could it be 1.51? I guess, right? But we took a random sample of 12 from that 162 to generate this number. So it should be in the neighborhood of that, right? So that's interesting. So we're going to say that for all 162 players, for each additional shot they take, on average, they're going to increase by about 1.5 points a game, or 1.51 points a game. So that's our estimate for beta. And now let's define what sigma is in context. So sigma is the amount our predictions of points per game will be off by. So sigma is the amount our predictions of points per game will be off by when using the true regression line, right? Because it's sigma we're talking about here. So sigma is the amount our predictions of points per game will be off by when using the true regression line, relating points per game to shots per game. Of course, we didn't calculate sigma, but we did get S, our estimate for sigma. So our estimate, and I might have erased it. I think I did, but I remember what it was. So our estimate for sigma is about 2.0 points. So what that means is if we had our hands on the true regression line and we used it to predict the points per game for a player based on how many shots they take per game, we're going to be off by 2 points on average, or about 2 points on average, since that's an estimate for the real number, which means sometimes we'll be off by more than 2, sometimes less than 2. Okay, so that's a measure of how accurate our regression line would be in making those predictions.